Hello everyone, and thanks for being here today. I'm Thibaut Dumont. I'm the chair today for this new seminar for IRENA, and I'm glad today to welcome Anish Amarsi from Uppsala University in Sweden. To introduce a bit Anish to all of you, Anish received his PhD from the Australian National University in 2017, working with Remo Collet and Martin Asplund. He then did a postdoc at the Max Planck Institute in Germany, working with Karin Lind. And as I said, he's now a researcher at Uppsala University, thanks to an individual starting grant from the Swedish Research Council. And so this evening, Anish will discuss about the abundances of the elements in stars, with especially the 3D non-LTE modeling. And so, if it's okay for you, Anish, I will let you share your screen, and I will let you the floor.
Right. Thanks, Thibaut. Yes, thanks a lot for that introduction and for the invitation to speak here. Yes, my name is here, Anish. This is the title of my talk. Abundances of elements in stars. How do we get them, and why should we care about the modeling? And I'll focus on this aspect here, the 3D, non-LTE, using 3D models and non-LTE modeling to get more accurate abundances of stars. All right, so let's continue. Here's a brief outline of my talk, so I'll try to stick to this, give or take a few minutes. Start with the motivation, why this is interesting, then focus on the theory and the methods. That's perhaps the main part of the talk. And then going on to some illustrative results for why, again, the 3D and the non-LTE modeling is important if you are interested in stellar abundances. And these illustrative results, I'll focus on carbon and oxygen in a sample of stars, and then I'll talk a bit about magnesium, which is more recent results. And then at the end, I'll go on to my conclusions very briefly. I'll stress here, if you have any questions during the talk, that is welcome, fine. Please try to interrupt me. I'm not sure how successful I will be in noticing. So
I will check for that.
Yeah, great, thank you. Thanks. But also, if you prefer to wait after the talk, should be fine as well. And then, okay, before I go on to the motivation, I'll just mention, and I'll show this at the end as well, that we recently had a review article. We worked on this article, and the preprint is on the archive. So if you want to know more about this topic, this is a very long article, so it has a lot of references and stuff that I simply cannot include in this 40-minute talk here. All right. Let's go on to the motivation then. So why should we care about stars? Well, many reasons, but the focus here today is this aspect that stars are kind of like fossils. They encapsulate the history of the universe, and you can use them to trace the evolution of the elements. And just one example of that is the sun. It's illustrated here on the right. So we have here on this plot atomic number on the x-axis and abundance on the y-axis. And just so everyone is on the same page here, this thing on the y-axis is the nuclear abundance in this form convention where H, hydrogen, is 12, as you see here. So if this X was H, then this would be exactly 0, so hydrogen is 12. But then all the other elements are some number less than 12. And even here for the sun, we see many interesting features in this plot. To begin with, for example, it spans 12 orders of magnitude. Okay, we have various peaks and also troughs and huge depletion of these light elements here. We also see the iron peak and various neutron capture peaks. We see a strong odd-even effect, and all of these things, of course, relate to various aspects of nuclear physics, but also to the history of nucleosynthesis in the cosmos. A lot of this nucleosynthesis happens in stars, or happens when the stars explode, but which is also interesting. But the relevant aspect here is that the abundances that we measure in the atmospheres of stars now can be used to trace this history and also to learn about nuclear astrophysics. Okay, so how do we go about getting these abundances? So the schematic here, we have the star emitting photons. We collect the photons with our spectrograph, we get the spectrum, and we convert that to the abundances that we're interested in, as well as perhaps some other parameters, stellar parameters. And from there, we interpret them and we learn stuff about the elements or about nuclear physics and so on. The key point for this talk is this step here, going from the spectrum to the abundances, right? So to do that, we need models, atmosphere models. And for the purposes of this talk, we will divide it, the modeling aspect into two. One, the atmospheric structure. So this is the 1D versus the 3D aspect, or the macrophysics. And then, if you like, the microphysics, the non-LTE aspects, so the interactions between the atom producing the spectral line with the photons and the electrons and the hydrogen atoms and so on. So just to put this in another way, the abundances that we measure are inferred by comparing the observed stellar spectrum to various theoretical model spectra. So illustratively, if the blue, for example, were the observed one and the red in this plot were the theoretical one, and everything else in the model was correct, then we could lower the copper abundance in the model until it fits the observed one, and that way you would infer the copper abundance. But the key thing here is that this works only if everything else about the modeling is correct. And assuming the stellar parameters are correct, you also still need to worry about the modeling assumptions. If the standard assumptions in analyses even today that the atmosphere, the stellar atmosphere, is one-dimensional and hydrostatic and in radiative equilibrium, and moreover that it satisfies a local thermodynamic equilibrium. So these things also will affect your line strengths, all right? And so the question for this talk is, to what extent do they, or well, to begin with, how do they, why might they affect the line strengths? And then to what extent do they affect the spectra and our interpretations? So that, yeah, sometimes I use this here, like a bullseye, kind of to make you think about this concept of precision versus accuracy. We want to get accurate results, but we might not be getting that with these 1D LTE models, right? And repeat observations, if you like, could increase the precision, for example, but if the model is incorrect, then we're still getting inaccurate results. Okay. So to talk about the theory and the methods, we can start here, for example. This is the sun. Observations of the sun, and if we zoom in on the atmosphere, it looks something like this. We see that the surface of the sun is granulated. Okay, we have these bright patches here, which are the granules, and then in between are the intergranular lanes. There's evidence of convection going on underneath the optical surface. So the granules are where you have the hot upflowing gas, and the lanes are where the gas the cool gas is flowing back down rapidly. And so these days, well, actually, I guess there's a lot of literature on this now, but people can model this. If you take model a small patch of the surface, so-called box in the star models, and then you can get, for example, something like this. Sorry, this is a simulation with the stagger code from Remo Colette. And we can do this not only for the sun, but for other stars. And for example, some K-giant here. And you can see in the surface on the top here, you can convince yourself that it looks a bit like that granulation feature that I was talking about earlier. And indeed, if you now do radiator transfer through the model and you get the intensity, you take a snapshot of that, you'll get something that looks like this. Actually, it's not a snapshot, we're evolving in time, I see that. And I point out just briefly that the movies are sped up by different amounts, but you see that all these stars with convective envelopes should have granulated surfaces, and then we can try to model them from first principles using these 3D hydrodynamic simulations. Now, if you use 1D hydrostatic models, you cannot predict these features at all. So this is one of the problems with 1D models. And if we now look at what happens to the spectral lines, because of that, can be helpful to distinguish between direct and indirect 3D effects. So if you like, this is a direct 3D effect. So here we have on the left a schematic of the granulation. So the granules here and the lanes here. So because we have hot upflowing gas here, it's hot, so the flux is higher, the spectral line being that we see in the granule. And it's also blue shifted because the gas is going towards the observer, towards us. Then in the lane, it's cooler, and so the flux is lower, and the gas is red shifted. It's going away from us. So they're summarized there. But what we see when we observe stars is the disintegrated flux. So that's shown in the final panel here, the solid line. What you see, what happens just because of this, the spectral line is skewed. So that's what this bisector here is meant to illustrate. The line is broadened compared to if you did not take this into account. So this thing here, and compared to the dashed line. And there's a net blue shift because the granules kind of dominate the surface. This broadening, by the way, would be interpreted as macroturbulence, but you can also have the same sort of thing on much smaller scales, and that would be contributing to another type of broadening, microturbulence. And these various broadening sources of broadening are a big problem in 1D analyses based on 1D models. It's another, yet at least one, sometimes several more free parameters that one has to worry about. Okay, we also have various other types of 3D effects. Now I'll just talk about this one here, which really shows up for metal poor stars in particular. So we have here a plot of the gas temperature on the y-axis as a function of depth in the atmosphere. So it's actually log optical depth at some reference wavelength. So here is the photosphere. Here is where the okay, so the effective temperature corresponds roughly to around here, and the continuum photons are escaping from around here, and then the spectral lines are forming around here typically. So the orange, or I guess it's orange, is the 1D model calculated with the same stellar parameters, but is assuming well, yes, with the same stellar parameters, and then the black distribution that you see in the background is the 3D model, calculated kind of in the same way as the 1D model, or maybe I should flip that around. And this dashed line here is what you get if you take the 3D model and you average it temporally and horizontally. And you see there is a temperature difference, right? The 1D model is too hot in the line forming regions, and this can be interpreted as missing the adiabatic cooling of the expanding granules in this region. So if we consider what happens to spectral lines, what we have on this plot on the right is the lines of NH calculated using the 1D model and using the 3D model for the same, everything else is the same in particular the nitrogen abundance, which is shown here, 4.83. And you see that the 3D model the lines are typically much stronger than the 1D model. And this can be interpreted simply due to this much cooler temperature of the 3D model compared to the 1D model, which facilitates much more molecular formation. So there's just simply much more NH in the atmosphere, even though the stellar parameters are identical in the two models. Okay, and with more N forming NH, then you get more stronger spectral lines. And then to quantify this error, you can repeat this spectral synthesis on the 3D model with a much lower nitrogen abundance. In fact, you lower it by more than 50%, and then, roughly speaking, the two sets of spectra agree. In other words, if you do a 1D analysis of the star and you try to get the nitrogen abundance from this set of spectral lines, you would overestimate the abundance by more than a factor of 2. Okay, so that's that for 3D. Now briefly about the non-LTE. Here we have a vertical slice of one of these 3D models. This is again gas temperature. This is on the x-axis is horizontal distance, and on the y-axis is vertical distance. Now, on the bottom panel, it's not gas temperature, but it's the radiation temperature at a particular wavelength divided by the gas temperature. And just to remind you, perhaps, in order to get the spectrum, what we are doing is radiative transfer through these models at different angles and different frequencies. And then in that way, we will get the spectrum that we're interested in. Now, the non-LTE-ness comes from this plot here, or was illustrated in this panel here. What we have is that the radiation is not that of the Planck function, right? So we have escaping photons, in particular at this wavelength, meaning that the radiation temperature in the upper layers is much larger than what you expect from the Planck distribution. Okay, so hot photons from the deeper layers are what you're seeing here. And this non-local radiation will interact with the matter and drive it away from local thermodynamic equilibrium. So to say that in another way, to get the spectrum, we need to know the populations, N, of the absorbers and the emitters in the atmosphere. And we can do this in general by solving for statistical equilibrium. So this is a fairly intuitive equation, I suppose. It's just everything that goes out of a level has to be balanced by everything coming back in. And we have radiative rates, R, and collisional rates, C. Okay. The radiative rates take into account both the local and the non-local radiation. And the non-local radiation is what drives things away from LTE. So in other words, if the collisions dominate, then we will get back into LTE. So LTE now in this would mean that the populations satisfy the Boltzmann distribution and the Saha equation and so on. So we have to solve this equation. If we relax the assumption of LTE, we have to solve this equation and see what happens. Okay. Apart from being computationally expensive and having to deal with convergence issues and so on, another challenge that should not be neglected is that this way of modeling requires much more data, atomic data, because we need now to know the energy levels and the radiative transition rates and the collisional rates and so on for all the levels of significance. In LTE, we don't need to worry about any of this. We can just model the line, for example, that we're interested in on its own. Okay, because the populations are already for this and for this are already known, essentially. And yes, so this is a challenging aspect of the work. It involves collaborations with atomic physicists to compute or to measure the missing data. And a lot of the data is missing, especially for heavier elements. That's why you'll see at the end, my examples are for light elements, which are kind of much more, the data is much better, and they're also typically cheaper to calculate the non-LTE solution. Okay, so then briefly, let's look at lithium a bit more closely. This is the term structure for lithium. We have the spectroscopic term on the x-axis, and then the energy of the various energy levels on the y-axis. So here's the ground state. And this is the resonance line at 671 nanometers. In the sun, if we use a huge lithium abundance, then the line might look something like this. So in 1D non-LTE, the line is much stronger than in 1D LTE. And why is that? This is fairly straightforward to understand, I think. You just consider the two levels themselves, and imagine that we are forcing the ratio of the populations to be in LTE, and then you suddenly relax that approximation, and then because the medium is starting to become optically thin, these photons can escape, and then the equilibrium reshifts such that you get a higher population of the lower level. So in other words, the photons just scatter out and are lost completely. And because of that, the line is getting stronger. If we instead contrast with this case here, so the sun is, for the purposes of this comparison, the sun is metal rich. This star, HD 140283, has the same effective temperature as the sun, but it's similar-ish log G surface gravity. It's a bit lower, but it's much more metal poor than the sun. And we see here a different situation. Although the line was getting stronger in non-LTE, the line is getting weaker. Sorry, although the line is stronger in the sun in non-LTE, the line is weaker in this metal poor star in non-LTE. That's this one here. Line is weaker than the LTE case. And the mechanism for this is a bit different. So we have, again, the term structure, and this is the line that we're interested in. And in this case, what's going on is that these warm photons from the deeper layers come in and interact with lithium, and are absorbed by the ground state, and that excites and ionizes the lithium in the ground state, so that the population of absorbers becomes lower, and in that way we get a weaker line. And this happens in the metal poor case because in the metal rich case you have more opacity to block these photons from coming in, so that effect is kind of hidden or blocked by the higher metal opacity in the sun. So the message here is that these non-LTE effects can vary strongly depending on the stellar parameters, and they, although I haven't described this, but they also vary depending on the element you're looking at and the spectral line you're looking at, and so on and so forth. So it's hard to predict exactly what will happen without doing the calculations. And lastly, before I continue with my examples, we want to do this non-LTE modeling in full 3D to get the highest accuracy. And this movie kind of just illustrates the line formation going on in a 3D model in non-LTE on the right, compared to an LTE on the left, and you can see qualitatively it looks much different. The line formation can extend to much higher layers, and there are correlations with these various features that you see in the 3D models, including these shocks and so on. So that's that for the theory and the methods. So now back to the motivation. So these abundances that we measure in stars are inferred by comparing the observations to the models. And we want to know if the 1D LTE models are good enough. Okay? In other words, could they lead to incorrect stellar characterization and incorrect interpretations? Or in another way of thinking about this, could the 3D non-LTE models help us uncover interesting new things? So let's talk about carbon and oxygen. And to begin with, where do these elements come from? So carbon and oxygen, as you may know, are formed in helium burning in massive stars, and they're released into the cosmos when these stars explode, for example. Carbon may also be created in lower mass stars, and this can cause it to have what looks like pseudo-secondary behavior. So that's illustrated in this plot here. And in these various plots that I'll show for the rest of the talk, I have this box, this 3D simulation here when I'm showing 3D non-LTE results. But I also have this caption here. So in this plot, we have carbon to oxygen on the y-axis, and oxygen over hydrogen on the x-axis. And with this square bracket notation, the sun is now going to always be at 0, 0. Okay. And what we see is a trend, and at low metallicity or low oxygen to hydrogen, what we see is a plateau, which is consistent with this picture of carbon and oxygen coming from helium burning in massive stars. But we do see an upwards trend, which is what I've called here a pseudo-secondary production, perhaps from AGB stars or low and intermediate mass stars at later times. Okay, but what I want to show now is what happens if we, instead of using 3D non-LTE models, we go to 1D LTE models. There is the plot again, 3D non-LTE, and now I will switch and show the 1D LTE result, and I'll keep this 3D non-LTE, this curve that I've drawn on top, I'll keep that there. If you go to 1D LTE, it looks like that, so we're back and forth a bit here, 3D non-LTE, 1D LTE. Then I overplot another curve, roughly, for the 1D LTE, and we see the mean trend looks very different, right? So so how when this was reported some 20 years ago, the interpretation was that this trend that you see in 1D LTE could be reflecting, for example, carbon-rich yields from the first stars. So there was some excitement about this signature, this trend of increasing carbon to oxygen towards lower metallicity. But with more advanced models, basically 3D non-LTE models, we see that this trend is actually just a systematic modeling error. Okay, there is no trend, at least down to this metallicity. Another interesting thing about these results is if you look again at these stars here in the thin disk. So actually, I can skip back to the 3D non-LTE plot. Here they are. And you'll see that if you go to 3D non-LTE, if you go to 1D LTE, the scatter increases quite a bit, right? So we can zoom in on these stars and see what happens. And also interestingly, some of them have confirmed exoplanet detections and some do not. So we can also separate the points like that. So on the left, we have 1D LTE and all those stars that we were looking at. The ones without planets are in black. The ones with planets are in blue. On the right is the same, but now using the 3D non-LTE results. And on the left, we see that the two populations, if you like, kind of overlapping. You cannot distinguish them. On the right, you see a hint that the stars with planets tend to have larger carbon to oxygen ratios. Okay, and you only see this in this case when you're using this more advanced modeling. So this implies that if you were to do a 1D LTE analysis, you would miss this potentially interesting signature, and you would get an incorrect trend. You would misinterpret your carbon and oxygen abundances. You would maybe say, perhaps conclude that we are seeing evidence of first stars giving off carbon-rich material in the early universe. Okay, then my second example was about magnesium. And as you may know, the Milky Way, some 10 billion years ago or so, merged with a massive dwarf galaxy, and perhaps several other galaxies. And the evidence for that coming from Gaia, of course, but even before that, there was some evidence for this based on abundances and the available kinematics. So I point to in particular this paper from Nissen and Schuster, who identified two halo components based on 1D LTE abundances, especially of magnesium, but also of other elements. So if we look at the spectra of two stars from these two populations, okay, so the ones with low magnesium abundances in red, and then the ones with high magnesium abundances here in green. These are for two stars with similar, everything else is the same, EF log G metallicity, but you see very clearly that the magnesium abundance is very different. And you also see it for silicon, which is another alpha element. And you see some signatures for other elements too, but you see that iron is more or less the same for these two stars. If you translate the spectra to abundances using 1D LTE models, we do see a separation. So this is the high alpha or the high magnesium component, and then we have the low magnesium component. And this is interpreted as the accreted stars that were accreted into the Milky Way halo. And here we have the tumor diagram. So the classification based on magnesium abundances, and then plotted here, and we see that the low alpha or the low magnesium abundances mostly have retrograde orbits, for example. Okay, so let's okay, now I want to show what happens if you do this, look at these stars again, but in 3D non-LTE. So here I've plotted these stars again. So this is the low alpha component, and here is the high alpha component. I've also shown some thin disk stars, but the focus is on these points here. So this is magnesium on iron on the y-axis, and iron on Fe on H on the x-axis. The low alpha accreted component and the high alpha in situ component there. So if I switch to 3D non-LTE, this is what happens. Again, with the box to indicate 3D non-LTE. So several interesting things happen to the scatter and the gradients, but today I just want to focus on this aspect here, this separation. So we see that what it looks like is that the low alpha component is separating into substructures. So these squares maybe illustrate that here. And that could be interpreted as maybe being due to multiple or reflecting multiple merger events and not just a single massive thing. And indeed, if we look here, we have it again. Now what's being plotted is iron on magnesium versus magnesium on H, but we still see this separation much more clearly in 3D non-LTE than in 1D LTE. And now if we look in the tumor diagram, it does turn out that these separated, these substructures do indeed separate out. There's one exception here, But this one also has weird abundances of, for example, sodium. So for the most part, it does look like the 3D non-LTE modeling can perhaps help us resolve substructures in this low alpha component, which is kind of interesting, kind of exciting. To understand a bit about what is going on, we can look at one star in particular. For example, this one here, HD 84937, which is a well-studied benchmark star, metal poor F dwarf. So kind of like the stars in this sample that I've been talking about already. And we can look at the abundances of magnesium that we infer line by line. So individual spectral lines of magnesium, we can analyze them separately and infer different values of the magnesium abundance from them. And this is what we get in 1D LTE. So there's these orange points. So here, this line on the x-axis, I should say, is the reduced equivalent width of the line, so a measure of how strong the line appears to be. And the y-axis is the magnesium abundance that we infer. Problem here is mainly that the magnesium 2 line in this analysis, the line due to ionized magnesium, is way above that of all of these other lines, which are due to neutral magnesium. Yeah, okay, we say that there is an ionization imbalance, and it amounts to almost 0.2 dec. So this is, well, for context, that is much larger than the dispersion that we were talking about in the previous plot. And even if you do 1D, still do an analysis in 1D, but you go to non-LTE, that makes things slightly better. The neutral magnesium, the abundances from neutral magnesium go up a little bit, and that from ionized magnesium goes down slightly. But there's still a significant imbalance. Really, one needs to go, in this case, to full 3D non-LTE to get ionization balance approximately. Okay, admittedly, it's not perfect. There is still an imbalance of 0.02 dec if I take the weighted mean of these various magnesium lines. And we ignore the strong saturated lines, which have other problems. But it's pretty good. And then the reason what's going on here is that we have, again, this photon pumping, these warm UV photons being absorbed by neutral magnesium and causing it to ionize so that the lines get weaker. And when the lines are weaker, the abundance, you need more abundance in your model to fit the spectral lines, so the abundances go up. And this non-LTE effect of over-ionization is in fact enhanced in 3D. If you remember this indirect 3D effect with the atmosphere being cooler in the upper layers. In other words, there is a steeper temperature gradient in the 3D model, and that enhances this over-ionization effect. And in this Nissen and Schuster data that I was showing earlier, those abundances were based on neutral magnesium. So they are sensitive to these effects. Okay, then that was that for my examples. So just to conclude, this was the question, are 1D LTE models good enough, and could we do better? And I showed these couple of examples for carbon and oxygen, where we saw a spurious trend in 1D LTE that goes apparently spurious trend in 1D LTE, or at least the trends are different compared to 3D non-LTE. We see this interesting signature in 3D non-LTE, not present in 1D LTE. Then for magnesium, as I just talked about, we have substructure appearing in the low alpha halo in 3D non-LTE, which is not so easy to spot in 1D LTE. And we have ionization imbalance in 1D LTE, sorry, here, that is mostly resolved in 3D non-LTE. So yeah, there are more examples, I suppose, that one could look at. And again, I then point you to this review article, for example, which is the preprint is on the archive. But I hope I've convinced you that this line of research, 3D non-LTE modeling, is interesting, and that we can learn new things about our galaxy, about the universe, by doing more of this. And yeah, I guess that's all I have to say. So thank you for your attention.